We are going to be talking about the energy required to change phases of matter through physical processes. This means how much energy does it take to go from a solid to a liquid, liquid to a gas, or vice versa from a gas to a liquid to a solid. There are a couple terms that we need to know before we begin. The first is latent heat of fusion. The equation for latent heat of fusion is Q, which is energy, or heat energy, equals mass times the change in heat of fusion. That symbol is delta, it means change. So latent heat of fusion is the amount of heat required to convert some unit of mass, whatever that unit is, or quantity, of a solid into a liquid or a liquid into a solid without changing the temperature, and that's the key. And I'll show you what that looks like later. This means that if I had, as an example, if I have 1 gram of ice at 0 degrees Celsius and I want to convert it to a gram of water at 0 degrees Celsius, or vice versa, from water to ice, ice to water, it would require 334 joules of heat energy being either absorbed if I want to go from ice to water, or energy released if I want to go from water to ice. That number, 334 joules, is a constant. All substances have known heat of fusion values. It would be an intrinsic property of that substance. So if I want to go from ice to water at 0 degrees Celsius, I would need to add 334 joules per that 1 gram in order to make that change happen. And you notice that the temperature didn't change. It's 0 to 0. So that's our practice problem. Let's figure out how much energy is required to melt 10 grams of ice at its melting point. Well, melting point is 0 degrees Celsius, and if I have 10 grams of it, that would mean that I would need 10 times as much energy versus the 1 gram. So that would look like this. So I have the equation, energy equals mass times the heat of fusion, and I want to know how much energy is required to melt 10 grams of water. Given the fact that that number 334 and the units are joules divided by grams, you can also write those units joules, grams minus 1, and that -1 tells you that it's in the denominator, and you saw that in the last slide. It's the same thing. So you figure out if it takes 1 gram to melt if it takes 334 joules to melt 1 gram, I would need 10 times that much energy for 10 grams. So in this equation, my grams cancel out with my grams. The only unit I have left is joules. Therefore, it takes 3,340 joules of energy in order to melt 10 grams of ice. The next term that we need to know is latent heat of vaporization. So vaporization is how much energy is required to go from a liquid to a gas, or vice versa from a gas to a liquid, again without changing temperature. You notice the equation is the same. The only thing that changes is the word VAP, or vaporization, instead of delta H of fusion. So same equation, Q equals the mass times the delta H vaporization. For water specifically, the vaporization constant is 2,260 joules per gram. So it takes, for every 1 gram of liquid water, it would take 2,260 joules to heat it all up and turn it into a gas. If you want to go from a gas to a liquid, you would have to release that much energy from the system. And if it's vaporization, we're talking about liquids to gases, gases to liquids, we're going to be at the boiling point, which is 100 degrees Celsius. So as an example, how much energy is required to vaporize 10 grams of water at its boiling point? So I have the same equation, but this time I want to calculate the energy for 10 grams at its boiling point, which would correspond to a constant of 2,260 joules per gram. Grams cancel out with grams. So if it takes this much energy for 1 gram, I would need 10 times that much, would be 22,600 joules of energy in order to take 10 grams of liquid water and convert it all into a gas at the same temperature at its boiling point at 100 degrees Celsius. Here's the heating curve that you picked up in class. So please write what I write. and I'm going to color code mine to be as clear as possible. I'm going to add some constants over on the left-hand column that I'm going to need to calculate this problem. The first set of variables that I'm going to need are the specific heats. So because I'm going from ice, which is solid, to liquid water, to water vapor, gaseous, each of those have a different specific heat. They can take on a different amount of energy. The specific heat for ice is 2.03 joules grams degrees Celsius. It's kind of hard to see. The specific heat of water, 4.184 joules grams Celsius. The specific heat of water vapor, or the gas form, is 2.01 joules grams degrees Celsius. I also need the latent heat of fusion, or delta H of fusion, for water, which is 334 joules per gram, and heat of fusion of vaporization, which is 2,260 joules per gram. I need all 5 of these constants in order to solve this problem. Let's talk about this graph. All right, so we have different sections. On the graph, it's showing how temperature is changing over time. I'm starting out down here at about, let's say, negative 37 degrees Celsius. So it's measured in degrees Celsius. And I'm going from negative 37 up to 0. I'm going to call this section A. You notice that it plateaus at 0 for a little while, for a certain amount of time. I'm going to call that section B. And then we continue changing temperature for a certain amount of time. I'm going to call that section C. We plateau again at 100 degrees Celsius. Call that section D. And lastly, we finish out at about, we finish out at about 130 degrees Celsius. So here I have plateaus corresponding with 100 degrees Celsius, which is the boiling point of water. And I have the other plateau on section B at 0 degrees Celsius, which is the boiling point of water. All right. So for section A, what I have to do, I have a change in temperature. I want to figure out how much energy is required to go from negative 37 degrees Celsius up to 0 degrees Celsius. During this process, the molecules in the ice are absorbing energy and breaking the bonds of each of the individual hexagons within that structure. So in this process, I can calculate energy by figuring out how much of the substance I have, the specific heat of the substance, and the change in temperature. That's the specific heat equation. When we start to plateau at section B, I no longer have a change in temperature. Well, that's what the definition of the latent heat of fusion was. With no temperature change, how much energy is required to go from its ice form to its water form or liquid form. So for this, the equation is going to be Q equals the mass times the delta H of fusion. And I know to use fusion because fusion is a gas to a liquid. Section C, I'm going between 0 and 100 degrees. Well, that's when water exists as its liquid form. So this is going to be in its liquid form. And I want to calculate the energy required for a certain amount of mass given the specific heat of water and this temperature change from 0 to 100. That's the specific heat equation. I forgot to write down here that the blue line is its solid version. And then we plateau again at 100 degrees Celsius. Well, the definition of the latent heat of vaporization states without changing temperature how much energy is required to go from a liquid to a gas. Well, I can calculate without a temperature change how much energy is required for the mass of the substance, delta H of vaporization. Lastly, after all of my substance converts to a gas, I have a temperature change again, so I'm going from 100 to 130, so that's a delta T of 30, change in temperature. I want to figure out how much energy for a certain amount of mass, given the specific heat of gaseous water vapor, and a temperature change, how much energy would it take to go from here to here. So I have the equations of each section, and this would be when my substance exists as a gas, right there. So here's my question. I am going to use the specific colors. Okay, here is my question. How much energy, I'll write it up here. Is needed to convert, let's say, keep it a round number, 10 grams of ice to water vapor. Okay. So because I have this graph, I have the temperature on the graph that I need. If you're not provided with a graph, then you'll need to be provided with temperatures. So that's my question. So this question is going to require 1, 2, 3, 4, 5 calculations and a total of those calculations. So firstly, I have segment A. I'm going to use the 10 grams of the substance. That's how much ice I have. I know the specific heat of ice is 2.03 joules grams Celsius. And my temperature, I'm going T final minus T initial. I'm starting out at negative 37, so that's my initial, and I end at 0. So I have 0 minus negative 37, so my delta T is going to be a positive 37 degrees Celsius. Q equals, or the energy needed to get from here up to here, 751.1 joules. Okay, so that's one segment. The second segment, my green line, I don't have a delta T, so I can't use the specific heat equation, but I can use the heat of fusion equation, which is Q equals the mass, which is 10 grams of the substance, times delta H of fusion, which is 334 joules divided by grams. Well, we've already done that calculation. We know that Q equals 3,340 joules because the grams cancel out. So that's how much energy it takes to get from here to here. And what that means is it's going to, all of my ice, once it reaches this point right here, will be liquid. So I will not have any more ice left. The third step, segment C, I need to calculate how much energy is required to get all the way up here from 0 to 100, so that's a delta T of 100. Well, I still have 10 grams of the substance. The specific heat, because I'm now in the liquid form, I use 4.184 because that's the specific heat of liquid water. And then I'm going 100 degrees. Grams, grams, Celsius, Celsius, so I'm left in joules. So that's 4,184 joules. So that's how much energy would require to get from there to there. The next segment, segment D, I don't have a temperature change, but I can use Q equals the mass times delta H of vaporization because I want all of my liquid water to vaporize into gas. Well, that takes time and that takes energy. So I have 10 grams of the substance and it takes 2,260 joules per gram because we're talking about vaporization going from a liquid to a gas. Well, we've already done that calculation. It's 22,600. And lastly, I ran out of room, so I'm going to write it over here. Sorry about that. I have a temperature change again. I'm going from 100 Celsius up to 130, so that's a delta T of 30. Well, I still have 10 grams of the substance. Because I'm in the gas phase, my CP of the gas will be 2.01 joules grams Celsius. And we've already figured out that it's a 30-degree temperature difference from 100 degrees Celsius to 130 degrees Celsius. So Q equals 603 joules. So all of my energies are going to be 751.1 joules, add, so this is a total energy, plus 3,340 joules, plus the 4,184 joules, plus 22,600 joules, plus 603 joules. So all of these equal the total energy required, or total energy needed to convert 10 grams of ice to water vapor. So that equals 31,478 joules, or 31 kilojoules. Done.